Hello folks. This lesson is going to talk about electrical power and lead on to a scenario where we're going to be actually able to calculate the cost of electrical power. So what is power? Power is the rate of doing work or transforming energy over time. You can see the formula here. Power is equal to work over delta T or delta E over delta T. We often use deltas at the beginning when we're looking at equations because it's the change in energy over the change in time. But there is a possibility that I'm going to drop the deltas at some point, because if your starting energy is 0 and your final energy is a certain value, then really you only need to know that second value of the energy, because the first one is 0. Same thing with time. Oftentimes, and I've mentioned this before, oftentimes your starting time is 0, so delta T actually just becomes 1 time, which is your final time. But we usually always start, just on the off chance that your energy change wouldn't start from 0, and your time value wouldn't start from 0, or whatever delta value doesn't start from 0. So it's always good to know what the original version of the equation is, but it's a possibility that the deltas are going to get dropped, okay? But the important thing here is that power is the rate of doing work over time. So if you think of what the units are for work or energy, it's joules, and the unit for time is seconds, so it's joules per second. The unit for power is named after James Watt. This is his lifespan. And James Watt was one of the people who revolutionized the steam engine. He improved it to a point where it could be used for pumping water out of coal mines, and eventually went on to revolutionize transportation with the steam engine on trains. So you often see the word watt in the real world. This is obviously a light bulb packaging here, and it says 45 watts. So that represents how many joules per second are produced, and also used, okay? So you can see here that it says the energy used is 45 watts. Now, often these are LED light bulbs. Older light bulbs used to be 100 watt or 60 watt light bulbs. And I have that example here. So a 100 watt light bulb would produce 100 joules per second. And this type of light bulb is considered to be fairly inefficient. The older style ones that dealt with filaments, and we talked about this in a previous lesson, or it might be a future lesson, on how heat is generated with a filament, and you're losing that heat to the environment. So not all of the energy is being converted from electrical into radiant, which is light heat. Therefore, that loss is basically you're paying for that loss. So you're going to need a lot more electrical energy to produce that 100 joules per second of light, because of the loss to heat. So how do we calculate power using voltage and current? Power, as you saw in the previous equation, was energy over time. Because we're working with electricity here, is there any way that we could convert that equation to be using voltages and currents instead? Because that would be very convenient if we could do that. So we've previously seen an equation when we were dealing with what voltage was. We had written voltage with respect to an energy value like this. So we now know that this is the equation for power. That has an E in it, right? So if we have an E here and an E here, we can substitute, and we get VIT over T instead of E over T. So now we're starting to get a power equation with respect to a voltage and a current. But look at what happens to these times. times cancel out and we end up with an equation for power just with voltage and current. So if you know the voltage that a load is using and you know how much current is passing through it, you can calculate the power of that electrical thing. So do the units, if we do unit analysis here, do the units match up? If we multiply volts and current, do we actually get watts, joules per second? So if we think of what voltage is joules per coulomb. If we think of what current is coulombs per second. And if we cancel out the coulombs when we multiply those two together, we end up with joules per second. So all of the units work here. So here's the type of question that you could be asked to solve. What is the current drawn by a 100 watt light bulb operating at a potential difference of 120 volts? Well, if we use the equation P is equal to V times I, we are given P, we are given V, we're looking for I, so if we rearrange the equation to get I by itself, we're going to divide P by V. The power is 100. The voltage is 120, and I'll just do this off to the side here. And that gives 0.83 amps. If we look at an example with a LED bulb here, an LED light bulb is said to use only 4 watts of power, but be as bright as a 100 watt light bulb. How much current will it draw? So this is the benefit of LED light bulbs, is they use a lot less energy, but they produce just as much light as a 100 watt light bulb. So in this case, we'd still be on a 120 volt circuit, so our voltage is still 120 volts. So we're basically using the exact same equation. P is equal to V times I. We're rearranging for I. The power used in this case is 4 watts. The voltage is 120 volts. So 4 divided by 120 is 0.03 amps. That's actually a periodical, but I'm just going to round it off to 0.03. So you can see that there's a lot less amperage being used in a LED light bulb than in a 100 watt regular filament light bulb. Now, is there a way to get power equation, a power equation using resistance as well? There's actually 2 different ways. So this will show us that we can get power equations for every scenario. We can get power equations where we're given voltage and current. We can get power equations using voltage and resistance. And we can get power equations using current and resistance. And it's basically, if you follow one column here, we'll do one column at a time. P is equal to V times I. But let's say we want to replace the I value. Using V is equal to Ri, the equation for Ohm's law, we can rearrange that to get I is equal to V over R. If we substitute the I into the power equation, we get V times V over R, which gives V squared over R. So now I have a power equation for voltage and resistance. If I start up the same way, but this time I just use the V equation, V is equal to Ri, to get rid of the V in the equation, you just replace V by Ri, you get Ri squared, and now we've got a power equation for resistance and current. So there's multiple versions of the power equation for voltage and current and resistance. But that allows us to solve any problem with electricity dealing with any one of those variables, or any 2 of those variables, I should say. So here's an example. What is the resistance of a 6 times 10 to the 2 watt kettle that draws a current of 5 amps? So if we look at what we're given here as variables, and at this point we might want to write them down so that we can really know what's going on here. So these are the quantities that we're working with, right? So we're working with current and resistance and power. So you would go to your formula sheet, find the equation that deals with current, resistance, and power, which is P is equal to R times I squared. Okay, and we're looking for R, so we're going to isolate R. And now if I put my numbers in there, I'll be able to calculate the final answer. Like so. I'll do that off to the side. And we're getting a resistance of 24, and the unit for resistance is ohms. Here's another example. What power is dissipated by an electric frying pan that has a resistance of 12 ohms and operates at a potential difference of 120 volts? So in this case, we're dealing with the power, resistance, and volts equation. Power, resistance, and volts is P is equal to V squared over R. And in this case, we're just looking for the power. I'm actually going to let you do this one. You're just basically plugging in the numbers here. Should be pretty simple, okay? And I'm just showing you examples of the different types of questions you can now solve using these equations. So how much does it cost for electricity? I went online and I took a look at the tables that deal with operating costs. Now, at the recording of this video, we are actually in the middle of the 2020-2021 pandemic, and there's been some concessions made regarding how much it costs for electricity right now. Normally, you have these charts that tell you what are the time of use prices for electricity. It is less expensive during certain times and certain days of the week. So usually on weekends and statutory holidays, your electricity prices are a lot less because you're on what's called the off-peak time. If you look over here, there's off-peak, mid-peak, and on-peak. Now, again, because we're in the pandemic at this recording, these three numbers are the same, but usually they're not. As you can see right up here, these are those same three prices for November 2019. Now, before I get to this table, let me just explain these circles here. From 7 p.m. through midnight to 7 a.m. is what's called off-peak hours. From 5 to 7 p.m. and 7 to 11 a.m., that's considered mid-peak hours, and on-peak hours is anywhere from 11 till 5. Okay, and that's during the summer. In the winter, you can see that it switches. All right, so that's what these three pie charts are showing, is when you're on the different peak times. So it's a lot less expensive to use electricity usually, if you look at the chart up here, at the off-peak time than it is for the on-peak time. So this is usually the way the electricity system works, and I'm using the most recent chart values here to show you that difference up here. So off-peak, 10.5 cents per kilowatt hour is how you read this. 15 cents per kilowatt hour, 21.7 cents per kilowatt hour. So again, a lot more expensive. It's more than double when you're dealing with the difference between off-peak and on-peak. Now, what is a kilowatt hour? And how do we use this to actually calculate how much electricity costs? So if you look at this question, calculate the cost of operating an oven for 3 hours if it draws 25 amps from a 240 volt supply at a rate of 15 cents per kilowatt hour. Well, let's first, we see kilowatt hours there. We'll talk about what that means in a second, but let's focus on the watts, okay? We know that power gives watts, right? And we're given a current and we're given a voltage. So let's start there. Let's calculate the watts with 240 volts and 25 amps. So again, I'll do this off to the side. So that's giving 6,000 watts. Okay, but this is kilowatts, all right? So we need to convert this to kilowatts. How do we do that? Well, to go from meters to kilometers is divide by 1,000. It's the same thing here. To go from watts to kilowatts, we're going to divide by 1,000. Okay, so that gives 6 kilowatts. Now, what we're going to do is we're going to look at the unit to guide us as to what we got to do next. These are kilowatts times hours. Well, they gave us the amount of time that this is working in. So we're now going to multiply the 6 kilowatts times the time to get our kilowatt hours. So that's going to be 6 times 3, which equals 18 kilowatt hours. And then to calculate the cost, since we know the cost is 15 cents per kilowatt hour, so we're really basically using unit analysis here to figure out how to generate the equation. We're just going to take our kilowatt hours and notice this is not kilowatts per hour, it's kilowatt hours. They're multiplied together. But because it's cents per kilowatt hour, if I multiply by 15 cents per kilowatt hour, you'll notice that the kilowatt hours cancel out. And the only value that's left is a money value. So if you want to write this as an equation, we can say that the total cost for this appliance is the amount of power times the amount of kilowatt hours, which is power times time, okay, and multiply that by cents per kilowatt hour. Now, what is kilowatt hours? We still haven't really answered that question. What do you get when you multiply watts times time? Well, just pretend for a second that we're just talking about watts, okay, not kilowatts. So what are watts? Watts is a power unit, right? But power comes from energy divided by time. If you multiply that by time, the times are going to cancel out, and what you get is an energy value. So kilowatt hours are an energy measurement. And the reason they do that is because if you didn't use kilowatt hours, you're actually using a very small amount of energy per load. Now, it's larger for an oven than it is for a cell phone charger, okay? But it's pretty small values. You'd be working with very, like usually decimal numbers if you didn't do this. So it's just to make it a little bit bigger numbers so that it's less decimal places to work with. That's really the only reason they went to kilowatt hours. And a house usually does use, well, actually, sorry, I should rephrase that. Your kilowatt values are replacing thousands of watts, okay? So your household is going to use thousands of watts over a month, let's say. But remember, cents are 0.0 0.15 values, so those are small decimals. So it kind of combines the two worlds where you're going to have thousands of watts being worked together and cent values multiplied together to make the numbers a little bit nicer to work with. Okay, so 18 times 15 cents is going to be 270 cents. Now, that's usually converted into dollars, and to convert cents to dollars, we just divide by 100. So it costs $2.70 to run this appliance for 3 hours. And that's it. So you've now seen how power is a measurement of energy with respect to time. You've seen the 3 other different equations for power based on voltage, current, and resistance. And we've also discussed how do you calculate the cost of electricity being used based on the voltage and the current. You could do this with any of the power equations. If we had given you the voltage and the resistance, you could calculate the cost that way as well. So you now have all of these new equations to be able to solve all of those different types of problems. Expect some questions to try from homework, and that's it for this lesson for today.